Hello, everyone. Okay, uh, can you hear me? Okay, cool. Thank you for attending the event. My name is Wengao. I'm a software engineer at Google with 5 years of experience in software development. Today, my topic is how to design a MapReduce system. We will have a Q&A session in the last 15 minutes. Cool. Let's start. Um, we will have 4 sessions. First, I will give you a brief introduction to MapReduce. Then we deep dive into the MapReduce framework and MapReduce execution process. Finally, we will go through some code implementation of a simplified MapReduce framework. All right, let's start our journey. So, what is MapReduce? MapReduce is a programming paradigm and an associated software framework that is used for processing huge amounts of data. The term MapReduce refers to the two separate and distinct tasks that the framework performs. The first is the map job, which takes a set of data and converts it into a key value pair. The second one is the reduce job, which takes the output from the map job as input and combines those data tuples into a smaller set of tuples. So why do we need MapReduce? Before we answer this question, let's look at a classic word count problem. The problem is that how to count the word frequencies of a document. A naive solution, I give it in Java code. We simply use a hash map to record the number of times we see a word. Okay, how to improve the performance for the previous simple questions? Let's say if we have multiple machines, how can we improve it? One simple optimization is that we can split the document into multiple parts. In this diagram, we split the document into multiple lines. Then for each part, we use one machine to count the word frequency of that part. Finally, we merge the results from each part to get the final output. Just a quick question. What is the drawback of this optimization? I believe some of you already found that the merge stage, the machine fault in this diagram, will become the bottleneck. Okay, let's further improve the performance. Now we have located the bottleneck, which is the merge stage. How about to parallelize in the merge stage too? It is not necessary to only use one machine to do the merge. We can use multiple machines too. We can dispatch the intermediate results by hashing the key. The same key will go to the same machine. Then the merge machine will aggregate the results for each key. The key assigned to it. Later on, the final output will be returned to the destination, say HDFS. In MapReduce, we usually write the output into the MapReduce, but it is not necessary to be the MapReduce. Sorry, it is not necessary to be the HDFS. Actually, the idea we mentioned above is what exactly MapReduce does. Let's do a small recap. In the map stage, in our previous diagram, machine 1, 2, 3 are responsible to map the input content to a list of word and count. key-value pairs. In the reduce stage, machine 4 and 5 are responsible to merge the key and list of value which are sent to them. Some questions. Who is responsible to split the original input, I mean the document or the input data set, into multiple parts and then feed to each mapper? And who is responsible to dispatch the outputs from mappers to reducers? Answer is straightforward. MapReduce Framework will take care of all this stuff for us. Cool. Now let's look at what exactly the MapReduce Framework is. Basically, there are 6 steps in the MapReduce Framework. Input reader reads data from the config input source, usually in DFS, and splits it into data chunks. Each chunk will be fitted to a mapper. And map function process, then we go to the mapper. Map function will process the data chunk and converts it into a list of key value pairs. Then we go to the partition stage. This stage assigns the output of each map function to the appropriate reducer by hashing the key. So the same key will be assigned to the same reducer. This is very important in the concept of MapReduce Framework. The same key will be assigned to the same reducer. Later, we will go to the shuffle and sort stage, which shuffles data within machines so that it moves out from the map and get ready to process for the reduce function. The sorting operation is performed on input data for reduce function. Then we go to the reduce stage. Reduce function is applied on each unique key. It iterates the values associated with the key and generates the corresponding result. Finally, the output writer writes the reduced output to the stable storage, for example, HDFS. MapReduce Framework has already done most of the work for us. We just need to focus on the launch of map function and reduce function for our business need. As you know, MapReduce Framework is executed as a distributed system. Put simply, the system contains a controller server and multiple worker servers. Now let's talk about the MapReduce execution process as a whole system. This diagram comes from the paper of MapReduce, I mean the original paper. Basically, there are also 6 steps in a typical MapReduce execution process. Step 1, the user program starts the controller and workers. Second step, the controller assigns the task to the map worker and the reduce worker. Basically, assign the map and reduce functions. Step 3, each map worker reads the splitted input data and do the map job on their machine. Step 4, each map worker outputs the intermediate result on their local disk. And step 5, each reduce worker fetches the data from the map workers and do the reduce work on their machine. The final step, step 6, reduce workers output the final output data. Of course, we always have some frequently asked questions. Let's take a look one by one. Do mapper and reducer work at the same time, or does mapper work first and reducer second? Answer: the mapper has to be finished before the reducer can run. What happens if a mapper or reducer is down during a run? The answer is quite simple. We just reallocate a machine to redo the failed task. Is it necessary to store the mapper output data on the DFS? What if it get lost? There's no need to store the mapper output data on the DFS. We can simply store the mapper output, the intermediate output in the mapper machines in their local disk. Because if the data lost due to the machine failure, we can redo the task by assigning a new machine. Where are input and output stored? The answer is simple too. It can be anywhere. Typically, the data is stored in the DFS, but there's no restrictions. Can mapper and reducer be placed on the same machine? Yes, it can. However, this is not a very good design, as mapper and reducer have a number of pre-tasks to deal with before they can do the actual work. We can make them process the pre-task in parallel by assigning them to different machines to improve our overall performance. All right, here is the most exciting part. Let's go through some code implementation of a simplified MapReduce framework so that you can have a better understanding how MapReduce framework works, especially the partition, shuffle, and sorting steps, which are taken care by the framework itself. The following code is written in Golang. The base framework in the following slides most of them comes from the MIT public course 6.824. For simplicity, we will implement a package called MR, which is short for MapReduce, that contains the core log for coordinator server and worker server. The package can run across multiple machines or in a standalone machine across multiple processes. The coordinator and workers communicate with each other via RPC calls. The package basically contains three primary files: the coordinator.go, worker.go, and RPC.go. Now, let's just quickly go through the entry points of the program on coordinator and worker servers. No dark match. In the main function, we simply create an instance of coordinator and periodically check whether the coordinator has finished its job. For the worker server, it is quite similar to the coordinator. But for the worker, we need to load the map function and reduce function first. As we stated in previous slides, the map function and reduce function come from the user code. The user put their business knowledge into the map function and reduce function and provide those functions to the MapReduce framework. Okay, now let's go to our main dish. In coordinator.go, we define the task type and task state. The coordinator maintains the states of all the map tasks and reduce tasks. Just like a state machine. Now let's take a look at the entry point of the coordinator. Let's take a look at the function make coordinator, which is called in the server main function. Make coordinator function takes two input parameters, the input file path and the number of reduced tasks to use. Inside the function, there are some ordinary works. First, we initialize the coordinator instance. Second, we clean up the working directory. Finally, we instantiate a HTTP server thread to listen RPC calls from the workers. As a coordinator, it provides a following API for workers. First, request task, which is used for worker to request a task from coordinator. It can be the map task or reduce task, as well as some other task type to assist our framework work as expected. And the coordinator also provides workers with request task finish and request task failed, which are used for reporting the task status. That's it. The coordinator, the launch for the coordinator is not very complicated. Now let's go to the worker.go. After the worker is initialized, it enters a for loop and keeps requesting task from coordinator until it receives an exit task, which is a signal from the coordinator to let the worker know now all the tasks are completed and the worker can exit gracefully. Put simply, in the for loop, the worker does following steps. First, it requests a task from the coordinator via RPC call. Then, if the task is a map task, it uses the map function to execute the actual map job. If the task is a reduce task, it uses the reduce function to execute the actual reduce job. If the task is an exit task, which means all tasks have been done, then the worker exits gracefully. Otherwise, the worker will sleep for a while and then re-enter the for loop and go through the process again. Now, let's take a quick look at how the worker executes the map task. It is quite straightforward. First, it reads the input content from the input file, and then it calls the map function with the file content as the parameter. The map function will return a list of key value pairs. Finally, it writes the key value pairs out to the local disk. We will deep dive into the right map output later, but let's move to the next slide. One important thing I need to mention is that for each key value pair, it will be written to different local file. The temporary file name looks like following: mr map task id reduce id worker id. The reduce id basically equals to the hash value of the key and then multiplied by the number of reduce. The map task ID and worker ID are deterministic. Those IDs, the map task ID and worker ID will be determined during the program's at the start stage. At the booting stage of the program. After all the outputs are flushed, the worker will rename the temporary file to mr hyphen map task id hyphen reduce id. This technique can make sure that if the worker failed or something wrong happened, the uncompleted result won't pollute the final result. You can check the file length carefully between the final file length and the temporary file length. The difference of those two file lengths is that the new one, the later one, eliminates the worker ID suffix. And we will only publish the final result when we are sure everything is okay. All right. Now let's also take a quick look at how the worker executes the reduced task. As usual, it is also quite straightforward. First, it reads the intermediate results from the mapper. Then, for each key that is dispatched to the reducer, it calls the reduce function with the key and the list of values as parameters. Finally, it writes the reduced results to the output location. As we mentioned in previous slides, the mapper writes the intermediate results to the local disk with file name mr-map task id-reduce id. Then the reducer just simply reads all intermediate files whose length matches mr-star-reduce id. It basically means it reads all the files that are targeted on this reducer. Let's do a quick recall. In the mapper, we calculate the reduce ID by hashing the key and then moduled by the number of reducers. So in each reducer, we can use the reduce ID to find the corresponding intermediate files, which should be assigned to the reducer. Cool. Thank you all for listening. Any questions? All right, cool. Thank you all for joining the event today. Hope the talk was helpful to all of you. Feel free to continue this discussion with me on the event page. See you. Take care.